Good day to you all. My name is Michael Greenacre and I'm here in this wonderful spot in central Catalonia. My route took me to this sign and it says in Catalan, No som més que les nostres decisions. In English that is, we are no more than our decisions. Well, I made a decision and my decision is not to use the most popular measure of sample difference in multivariate ecology, and that is the Bray-Curtis dissimilarity. Of course, this is a free world and you're welcome to use it if you like. But let me tell you the reasons for my decision.
Well, after that walk, let's have this talk, which might turn out to be a little bit controversial and cause some debate. Anyway, I like to start talks like these with limericks, and I'm going to give you 3 limericks as a summary of my talk. 2 botanists called Curtis and Bray came up with an idea one day. To distinguish samples A and B, let's invent a dissimilarity, which their essential difference will convey. The idea was simple, as you'll see, so Bray-Curtis gained popularity, but count data being notoriously skew, transformations they had to do to balance high counts with rarity. But for me, on closer inspection, their indexes gained disaffection. When large count ranges are found, size and shape differences do confound, which, after detection, lead to Bray-Curtis rejection. The key words here are dissimilarity, skew, transformations, size and shape, confound, and these will be dealt with in turn. So let's get started. First, what's this all about basically? Why dissimilarity, distance, multivariate, and so on? In certain areas of ecological research, we could have count data, for example, species abundances in a set of samples from transects, quadrats, or volumes. The data could also be biomasses, and then what about all the environmental parameters? We'll stick to species abundances for this talk, like the stations by species data set shown here. If we just had one species, that is univariate data, then comparing samples is simple. To compare multi-species samples, we need to be able to measure differences between them. These differences will allow us to know which samples or sample groups are similar and which are different. This proximity measure, once we have it, then we can achieve a low-dimensional ordination, like a map of the samples, or alternatively a clustering. So this proximity measure is essentially the multivariate generalization of a simple difference in the univariate case. Now I'm going to talk mostly about the Bray-Curtis measure of dissimilarity and contrast it with other measures, for example the chi-squared distance. Notice the one is a dissimilarity and the other is a distance. This will be made clear later. My question will be, what is the nature of the difference that Bray-Curtis is actually measuring between 2 multivariate samples? I've read so many times in the literature that Bray-Curtis is a measure of compositional difference. For the last 20 years, I've been working in the field that's called compositional data analysis, and it has become clear to me that the word compositional, used by many authors in the Bray-Curtis context, is not what I understand by this term. Notice too that this choice of proximity measure is fundamental to everything that is done afterwards. Unfortunately, in software like the R function vegdist in the package vegan and the commercial package primer, the Bray-Curtis dissimilarity is the default method. So I suspect many users simply accept this default as if it's what they need. Take a look at what the primer manual says. It first of all gives Bray-Curtis dissimilarity as the first option, and then the manual says relevant defaults will be suggested given the data type. For example, measure is Bray-Curtis for biota and measure is Euclidean distance for environmental variables. I wish there was no default specified, so users would have to think a bit before they make their choice. Certainly enhanced by this type of promotion, the Bray-Curtis dissimilarity has become one of the most popular proximity measures in multivariate ecology. All the data have to be on the same scale. For example, there are counts in this data matrix shown here of 30 sites by 5 species. To compute the Bray-Curtis between sites 1 and 2, for example, first sum the rows to get total counts of 27 and 54. Then add up the absolute differences, that is a difference of 26 on species A, 2 on species B, 4 on species C, and so on, giving a sum of 37 differences between the sites. Then the Bray-Curtis dissimilarity is simply the 37 divided by the total counts in the 2 samples, that's 27 plus 54, and that gives a value of 0.4568, often expressed as a percentage, 45.7%. Notice that Bray-Curtis is 0 when the 2 sets of counts are exactly the same, and is equal to a maximum of 1 or 100% when there is no overlap between the counts. That is, wherever there's a positive count in one sample, the corresponding value in the other sample is 0. While ecologists might not be sure exactly what Bray-Curtis is measuring, they are happy with a measure lying between 0 and 1, and that feature contributes to its acceptance. Computing the measure for all pairs of sites leads to a triangular matrix of dissimilarities, and the ringed value there is the one we just calculated. Notice in the formula for Bray-Curtis that the sum of absolute differences in the numerator is nothing else but the Manhattan or city block or L1 distance. Often Bray-Curtis is applied to a matrix that has constant row sums, in which case it is misleading and a distractor to call it the Bray-Curtis, when it is really the Manhattan divided by a constant. One obvious and recognized problem with Bray-Curtis is that there will be large between-species differences for more frequent species, which will then dominate the measure. So a transformation is required to compensate, often a square root or fourth root or log 1 plus x, which is a rather ad hoc decision with no clear way of deciding which should be used. For example, why is it always a square or a fourth root and never a cube root? Although the Bray-Curtis definition has an understandable scale for the untransformed data, which adds to its popularity, getting a handle on it is not at all clear for transformed data. For example, what does a Bray-Curtis value of 50% mean for fourth root transformed counts? The division by the sum of the counts, or usually by the sum of root transformed counts, is an attempt to make the measure compositional. But as I will explain, this doesn't always work out like you might expect. For comparison purposes and as a contrast to Bray-Curtis, I explain now what the chi-square distance is, which is also popular amongst researchers who use correspondence analysis, either the unrestricted form or the constrained form called canonical correspondence analysis, or CCA. In a preliminary step, the values in each row are divided by their row sums, and these row sums are what I call the sizes of the rows, thus eliminating the size differences and transforming counts in this example into relative counts called profiles. In addition, the column totals are also relativized in the same way, giving what's called the average profile. In the language of compositional data analysis, the profiles and the average profile are all compositions, summing to the constant 1. I say that these compositions describe the shape of the counts, their highs and their lows, not directly affected by their sizes. But these compositional profiles may be related to the sizes, of course. To make a simple analogy, big fish do not always have the same shape as small fish of the same species. To compute chi-square distance, let's look again at the first 2 sites. The square of the chi-square distance, that's the chi-square distance squared, is the sum of the square differences between the profile elements, where each square difference is divided by the corresponding element of the average profile. These terms are summed, in this case between sites 1 and 2, giving a value of 1.297, and then the square root is taken to get back to the distance of 1.139, which is the first value in a triangular matrix of distances between all pairs of sites. Notice that the division of each squared difference by the average or expected value is the chi-square distances way of compensating for the frequent versus rare relative counts. There are solid theoretical reasons for this type of standardization. Also, the distance is very similar to Euclidean distance, just with the added insertion of these compensating weights, which is why I call the chi-square a special case of a weighted Euclidean distance. Now, to contrast these two approaches to measuring multivariate proximity, let's take a very simple example of two rows of counts. The first row has counts 1, 2, 3, 4, 5, totaling 15, and the second row has exactly double the counts, 2, 4, 6, 8, and 10, totaling 30. These are two samples with exactly the same shapes, but different sizes. Euclidean distance is the square root of the sum of square differences equal to the square root of 55. The Bray-Curtis is the sum of absolute differences divided by the total count in the two samples equal to 15 over 45, which is a third. And the chi-square distance first divides out the row sum, so it gets exactly the same shapes, and so it is 0. If the data are log transformed, Bray-Curtis is 0.266. And if the data are fourth root transformed, Bray-Curtis is 0.086. Of course, if one divides out the row sums to get profiles, then we get identical rows of relative counts, and any measure of dissimilarity or distance is 0. Two important conclusions from this very simple example. When the shape of two samples is identical, Bray-Curtis still measures a difference between them, totally depending on their sizes. And secondly, a stronger and stronger root transformation is just bringing all positive numbers closer to 1. And if there are 0 counts, the strong root transformation is bringing the data set closer to a presence-absence one. Now I'm going to really rub all of this in. So here are some first take-home messages. Bray-Curtis is affected by the difference in the sizes, that is, the overall abundances of the samples being compared. It follows that Bray-Curtis only makes sense for samples taken from equal transects or equal areas or equal volumes. But even in such physically equal sized samples, there are inevitably differences in overall abundances. And these differences also count to a greater or lesser extent in the dissimilarity. A data set we will look at shortly has total counts from a minimum of 54 to a maximum of 13,065. Now let's look at a variation of this simple example by simply interchanging two pairs of counts, swapping the 2 with the 4 and the 4 with the 8. We now have two samples with different shapes and practically identical sizes, the row sums being 22 and 23. Since the absolute differences remain identical, and also the total counts in the two samples, both the Euclidean distance as well as the Bray-Curtis do not change. So now the Bray-Curtis value of 1/3, which measured pure size difference before, now measures pure shape difference. Anticipating my conclusion, the main reason why I don't use Bray-Curtis is that you are not sure how much a particular value is affected by the size part of the sample difference and the shape difference. On the other hand, computed on the relative abundances, which is pure shape, we're now getting some positive values measuring the shape difference. And remember that Bray-Curtis now reduces to the Manhattan distance. Well, I could stop this talk right now. The point is already being made in these two extreme cases. But let's add some more take-home summaries and then dig a little deeper into this issue. Bray-Curtis can, in extreme cases like the ones I've shown you, be measuring just a difference in total abundances or measuring just compositional difference in the relative abundances. In practice, it will be a combination of both. And if it is used on data with constant sums, there's no need to call it the Bray-Curtis dissimilarity. It is then a well-known distance function. And then what about this dissimilarity versus distance story? Bray-Curtis is not a distance, since it does not obey the triangular inequality. Hence it is called a dissimilarity or a semi-metric, and part of its variance cannot be visualized in our Euclidean world with its Cartesian coordinates. Most likely for this reason it is often subjected to non-metric multidimensional scaling, not a metric scaling method. Paradoxically, the metric properties of the non-metric scaling coordinates are then used to correlate with species and environmental data. On the other hand, a Euclidean type distance such as the chi-square distance has very favorable and familiar properties such as Pythagoras' sum of squares theorem and the decomposition of variance. And the decomposition of variance is pure Pythagoras. Up to now I've talked about size and shape using extreme examples, but in practice, is it possible to decompose any proximity matrix that measures between sample differences into parts that are size and shape? Well, these won't be possible to separate strictly, since there will almost always be a relationship between the composition of a sample and its overall abundance. It is possible, however, to quantify the following variance components, thanks to an idea by Burckhardt, Legendre, and Drapeau, who separated spatial and non-spatial variance components. We can separate it first into a part that is strictly size, uncorrelated with shape, then a part that is strictly shape, uncorrelated with size, and then thirdly, a part that confounds both size and shape. There could also be a residual part of the variance. The function Adonis in the vegan package is just what we need to compute these parts. So here is some R code to do it. Here I'm using a data set of 41 fish species abundances in 158 samples from the Barents Sea, based on 15-minute trawls. First, the univariate size variable is just the row sums of the data matrix fish, and the multivariate shape variables are the relative abundances, dividing each row by the respective row sum. The Bray-Curtis dissimilarity matrix is computed using function vegdist in the R package vegan, which has Bray-Curtis as the unfortunate default, as I mentioned, reinforcing its choice by the user. Notice that the range of sizes is very wide, with row totals from 54 to 13,065. There are four components of the dissimilarity that are computed: A, size not shape; B, size and shape confounded; C, shape not size; and D, a residual part, with A plus B plus C plus D summing to 100%. I won't go through the whole code, except to point out the results for this example: 3.8% pure size, 4.7% size and shape confounded, 71.3% pure shape, and a residual of 20.2%. These four components can be shown as a compositional bar plot. In a similar way, the same computations can be made using the chi-square distance. Notice on the right that the pure size and residual components are completely eliminated. But there is a small part of 2.5% that confounds size and shape. Otherwise, 97.5% of the distance measures pure shape, or what I call composition. As I say here, that 2.5% size and shape component for the chi-square gives a realistic idea how much shape is related to size, which is not very much in this data set. But the part due to size increases to 8.5% in the Bray-Curtis, and that pure shape component reduces to 71%. with a large residual measuring something else that we are not aware of. It would be very interesting to know what that residual part is, but it is partly due to the dissimilarity nature of the measure, which is not Euclidean embeddable and thus incompatible with the notion of variance. My conclusion here is that with the chi-square, I know very well what I've got, what it is measuring. In this case, almost pure composition, which is by design. But in the case of the Bray-Curtis, what it is actually measuring is much less clear, and a bit of a hodgepodge, which is an English expression that means a confused mixture. Time for more take-home remarks. We can measure the components of what I call pure size and pure shape, as well as the component affected by both size and shape. In empirical data, the component of size, including the size and shape confounded part, can range from about 5% to about 30% based on my experience. Multivariate analysis is used to relate the sample differences to differences in environmental parameters or to compare groups. It will be difficult to know how much these results have been influenced by the totals in each sample as opposed to the sample compositions. As a final example, consider the use of Bray-Curtis in a real experimental situation, where I maintain that one of the conclusions is possibly incorrect or at least misleading as a result. An ecotoxicological experiment was run with 30 sampling units, distributed randomly across 3 treatments. 10 units for a control labeled as C, 10 for treatment 1 labeled as T1, and 10 for treatment 2 labeled as T2. Each sampling unit was characterized by the abundance counts of 45 marine species. Using the Bray-Curtis dissimilarity on square root transform data, a significant overall group effect was found, p less than 0.001, again using the Adonis function. Doing post hoc comparisons of treatment groups T1 and T2 versus the control C, again using Bray-Curtis, both are found to be statistically different from the control at the 5% level. P is 0.048 and P less than 0.001 respectively. Bray-Curtis was specifically stated to be testing differences in community composition, and the conclusion was that significant differences in community composition were found between the control and each treatment. The $64,000 question is, what is meant by community composition? Looking close at the data I have, however, it was found that there were statistically significant differences between the total abundances in the 3 groups. See the box plots of the 3 sets of observations shown here on the right. The treatment groups had generally lower counts than the control group. As we have seen, these differences are contained to a certain extent in the Bray-Curtis dissimilarities between the groups. Using the coin package in R, a univariate permutation test indeed shows highly significant differences in mean total counts between the 3 groups, p is equal to 0.003, as well as between each treatment group and the control, with small p-values of 0.029 and 0.009. The question is, how much these differences in abundance levels have influenced the finding of the above significant difference in the so-called community composition using the Bray-Curtis? Or maybe that is the only difference between the groups. This particular example is special because the number of variables is larger than the number of samples. So the shape variables explain all the variance. So there's no residual variance and there's no pure size component. By the way, this point I missed in my article on size and shape, and there's a small computational error there, which luckily doesn't affect the conclusions at all. To measure the effect of size, we have to look at the percentage of size that is confounded with shape. The pure shape components of Bray-Curtis and chi-square are 84.7% and 93.4% respectively. Expected to be higher for chi-square since it is focused on shape. The size-related components are 15.3% and 6.6% respectively, and that difference of about 9 percentage points represents the additional size effect that is incorporated into Bray-Curtis. It is found that using the permutation test following the canonical correspondence analysis, the CCA, which uses the chi-square distance, that treatment T2 is significantly different from the control, as we found for Bray-Curtis, whereas T1 is not. P-value is only 0.039. So we have the situation that T1 is significantly different from the control using Bray-Curtis, but not using chi-square. And T1 also has significantly less total abundance than the control. My personal belief is that the difference in total abundances between treatment T1 and the control, which is incorporated more directly into the Bray-Curtis measure, led to the conclusion that T1 was significantly different from the control. There's in effect no significant difference in what I regard as composition. Let's summarize these results by looking at some multivariate ordinations of the Bray-Curtis dissimilarities and the chi-square distances. Added to these, I've put 99% bootstrap confidence ellipses for the group means, as described in my paper in Polar Biology on visualization of ecological data. Usually, non-overlap of these ellipses implies significant between-group differences, although it is best to compute the p-values to confirm. On the left for Bray-Curtis, the p-value between groups T1 and C is significant, and we can see that the ellipses do not overlap. Remember the difference in the sizes, according to these box plots. On the right, for chi-square, the p-value is non-significant, and the ellipses are overlapping. That is, the ellipses between treatment group T1 and C. So, as you see in the box plots in the middle, the univariate between group test reported a significant difference in total abundance between T1 and C, and that is what I propose is the real reason for the significant difference between T1 and C using Bray-Curtis. This is a further illustration that the shape or compositional difference between T1 and C is not statistically significant, whereas the fact that size is contributing more to the Bray-Curtis accentuates the difference between T1 and C and leads them to being significantly different. Soon I will conclude this presentation by recommending that size and shape be investigated separately, but maybe I'm misunderstanding what ecologists mean by community composition. Would they really prefer to have size and shape confounded in one measure of sample difference? And if so, does that mean that it's okay to use Bray-Curtis? Well, in this case, I see no justification for using Bray-Curtis either, because there are much better behaved true distances, alternative ones, that also confound size and shape, and I would prefer to use them. Here are two alternatives coming up. The first and the most obvious one is simply to use Euclidean distances on log transform data, of course with no standardization after log transforming. For count data with zeros, one has to be added before logging. The corresponding ordination using redundancy analysis is shown here. The T1 and C ellipses do not overlap, and a permutation test shows them to be significantly different. Another option, little used up to now, uses what I call the chi-square distance on raw data, which I published in the journal Ecology in 2010. This distance operates just like the regular chi-square distance, but does not relativize the data initially by dividing by the row sums. That is, raw counts standardized in the chi-square way are analyzed, and so the size is not removed. Again, T1 and C are shown to have non-overlapping ellipses, and the low p-value confirms that they are statistically significant. To my way of thinking, one of these is much better than using Bray-Curtis, if you think of overall abundances as an integral part of what you understand by community composition. And they are both Euclidean type distances. I might add that if the real experimental difference between a treatment and a control was only that it reduced the overall abundances of my species and not the relative abundances, I would certainly like to know that. Time to conclude by summarizing the previous take-home messages and some additional ones. Some general remarks. Be aware of the size and shape components in the measurement of multivariate proximity. I would recommend to separately study and test the effects of size, that's a univariate test, and shape, a multivariate test, in the analysis of data such as these, abundances, biomasses, and so on. Make a univariate permutation test of size effects, e.g. of total abundances or of species richnesses, and then you make a multivariate permutation test of the shape effects using chi-square distance inherent in CA or CCA, or other distances that measure only shape, such as Hellinger or log ratio. And now some specific conclusions about the use of Bray-Curtis. Bray-Curtis dissimilarity is not a well-defined distance, which clashes with the concepts of metric methods of analysis. And it measures both size and shape differences unless the sizes are constant across the samples. Conclusions using Bray-Curtis can thus be affected by differences in sample totals, what I call the sizes. If you really do want to analyze size and shape jointly, there are alternative Euclidean type distances. As I said before, it's a free world, but be aware and be wary of Bray-Curtis. I've decided that there are other options and more favorable properties and less ad hoc decisions to be made along the way. So this is why I decided not to use it. I give some references here as well as to my books. Much of what I presented and more is in my article in Methods of Ecology and Evolution in 2017. Take note of the site multivariatestatistics.org, where you can download some of my open access books, including the one based on the course Multivariate Analysis of Ecological Data. I also repeat the limericks that I gave at the start, since they essentially summarize the message of this talk, as well as my email address and various web pages. A recurring theme in all of this is to try to understand what ecologists mean by community composition. In one of her papers, Marty Anderson says, speaking about the Bray-Curtis dissimilarity, an important ecological issue is to understand how much of the dissimilarity is driven by compositional difference and how much is driven by differences in relative abundance, which is difficult to ascertain for the Bray-Curtis and related measures. Well, already with that statement of hers, I'm confused, since I understand compositional difference to mean difference in relative abundances, taking my cue from compositional data analysis, of course. What I've tried to do is to show how much Bray-Curtis and other measures are driven by what I understand by compositional differences, that is shape, and differences in overall abundances or sizes. I hope we can clarify the terminology and objectives in the future. Thanks very, very much, and I invite you to keep in touch.
Well, after that walk and the talk, I'm enjoying a nice Catalan tallat, which is the same as a Spanish cortado, and I hope you enjoyed the talk, and well, good luck with all your multivariate analysis, and let me know how you're doing. Bye-bye.